Harwig, a senior in ME. I'm the group lead for Group 2, Experiment 4, the Rankine cycle. A quick introduction. Thermodynamics is the study of energy in terms of converting heat into useful work or power. William Rankine was a Scottish civil engineer, one of the founding fathers of thermodynamics. He created a theoretical process that is still used today for most of the world's production of electric power. So the goals of this experiment is to understand the operation of the Rankine cycle, to measure the volume of the condensate drain and the volume of the water drain from the boiler, and calculate parameters associated with the performance of the Rankine cycle, including the thermal efficiencies, temperatures, state data, and a few more. So what is the Rankine cycle? It's a cycle that produces electric power through 4 phases or steps. The first step, water is pumped into a boiler. The second one, the boiler is heated. The water is changed into a high pressure steam. The steam is then shot out into a turbine, which sort of acts as a generator and produces the electricity. And then the steam goes out into a condenser, and it turns it back into water, and it pumps it back into the boiler to start the cycle over again. So the cycle is a closed-loop system where water is the working fluid, and there are 4 major parts of the system: the feed water pump, the boiler, the steam generator, or the boiler or steam generator, the steam turbine, and the condenser. So we have an ideal versus real Rankine cycle, and here you can see sort of the temperature and entropy graph of them compared. But for the ideal Rankine cycle, it consists of a reversible process, and so that means that there will be no fluid friction and heat loss due to the surroundings. That's sort of in a perfect world. So it'll have a higher efficiency due to its isentropic process. But in the real Rankine cycle, you'll have some irreversibility processes such as the friction of the fluid, and you'll have heat loss due to surroundings. And so you'll have a little bit of a lower efficiency. So here's a little chart of the ideal Rankine cycle, or just a Rankine cycle. The boiler creates a heat source, QA, the heat generated in the boiler, and that's sent to the turbine where it's produced the steam, and it produces the work of the turbine, which is the energy, and then the steam is sent into the condenser where heat is taken out of the system, and it's turned back into a liquid where the pump produces work to pump it back into the boiler. Some steam is lost, so supplementary water can be added into the system. Here's an energy analysis of those 4 processes. For the pump process, the work is equal to the enthalpy at position 2 subtracted by 1. The boiler, the heat energy added is equal to enthalpy at position 3 minus 2. Turbine, the work output is equal to enthalpy of 3 minus 4. And the condenser, the heat rejected is enthalpy of 4 minus 1. So here's a PV and a TS diagram of an ideal Rankine cycle. And you can see the 4 processes going around both of those. So the overall energy balance, you have the heat in minus the heat out, subtracted by the work of the turbine minus the work of the pump is equal to 0. The overall thermal efficiency is the work of the cycle divided by the heat added times 100, or you can use the enthalpies to solve for it as well. So here's the apparatus of the lab. A few things to note: you have the condenser tower, the sort of tall golden one. The turbine is sort of in the middle right there. You have the generator in there as well, the boiler, which is heated by the propane tank. That's just sort of the main parts of that. Data will be collected using the computer on the left side. So the predicted results, there's quite a few of them, so I won't hit on all of them, but there'll be about 6 to 8 plots that you'll have to use, pressures and time, or pressure and temperature versus time graphs of the boiler, turbines, and from those plots you'll calculate inlet and outlet pressures and temperatures of the turbine. There's some flow rates, and also steady state data. And using that, you'll be calculating the thermal efficiency of the cycle. And for a real Rankine cycle, it should be around 30 to 40%. A few uncertainties of the experiment will be the heat loss due to the surroundings, the fluid friction in the piping, and lastly, human error measuring the volume of the condensate of the water from the boiler drain. There's my references. That's it.